Picture this. It's 1967, and a Camaro Z28 screams past 7,000 RPM coming out of Riverside's Turn 9. The driver downshifts hard into the S's, the tachometer needle swinging violently toward 8,000. There's a sound like a shotgun blast. Oil sprays across the track. The engine compartment fills with smoke as a connecting rod punches through the block, taking half the oil pan with it. The driver coasts to the infield, his race over, his engine destroyed. This wasn't unusual. This was Tuesday for the 302 turbo fire. They called it the DZ302, and it might be the most misunderstood engine in Chevrolet history. On paper, it was a marvel of high-revving engineering, a destroked 327 that could spin to 7,000 RPM and make power all the way there. In reality, it was an engine that ate itself alive with disturbing regularity, earning a reputation as one of the most fragile power plants ever to wear a bow tie. This is the story of how Chevrolet built a racing engine for the street, forgot to tell anyone how to actually run it, and created a legend built on broken parts and shattered dreams. To understand how the 302 became synonymous with catastrophic failure, we need to travel back to 1966. The Sports Car Club of America had just created the Trans Am Racing Series, and there was a problem. The rulebook specified a maximum displacement of 305 cubic inches, or 5.0 liters. Ford was ready with their 289. Chrysler had their 273. Chevrolet? They had nothing. The smallest V8 in their lineup was the 327, and that was 22 cubic inches too big. Vince Piggins, Chevrolet's performance products manager, had a solution that was elegant in its simplicity. Take the 327 block and stuff in the crankshaft from a 283. The shorter 3-inch stroke would bring displacement down to 302.4 cubic inches, just under the limit. But here's where it gets interesting. This wasn't just about meeting rules. The short stroke meant the engine could rev higher than any production Chevrolet V8 before it. We're talking about pistons that could change direction 14,000 times per minute without exploding, in theory. The engineering was actually brilliant. The bore measured 4.0 inches exactly, same as the 327. But that 3-inch stroke created a bore-to-stroke ratio of 1.33.1, what engineers call over square. This meant the pistons didn't have to travel as far on each stroke, reducing stress and allowing higher RPM. The combustion chambers were more efficient too. That wide bore gave the valves room to breathe, while the short stroke kept the flame travel distance manageable. Chevrolet's engineers didn't stop there. They knew this engine would live at high RPM, so they fitted it with a mechanical camshaft that would make a NASCAR engine blush. The legendary 3030 cam, part number 3849346, featured 0.485 inches of lift and 254 degrees of duration at 0.052-inch lift. Those numbers might not mean much to you, but consider this. A typical street cam of the era had about 0.390 inches of lift and 2 to 10 degrees of duration. This thing had valve timing so aggressive that it barely ran below 2,000 RPM. It would stumble and cough at idle, like it had tuberculosis. The intake valves measured 2.02 inches, the exhausts 1.60 inches, big for the era, especially in those small combustion chambers. The valve springs were rated at 300 pounds on the seat, compared to about 80 pounds for a regular passenger car engine. They had to be that stiff to control the valves at 7,000 RPM. The rocker arms were stamped steel with a 1.5.1 ratio, pretty standard stuff. Too standard, as it turned out. Compression ratio was set at 11.01, which meant this engine absolutely required premium fuel, the good stuff, 100 octane or better if you could find it. Run it on regular, and you'd hear death knocks that sounded like someone hammering on the pistons with a ball-peen hammer. The pistons themselves were forged aluminum from TRW, designed to handle the stress of high RPM operation. The connecting rods were forged steel, 5.7 inches long, with 11 32-inch bolts holding the caps on. Remember those bolts. They're important. The cylinder heads were based on the new for 1967 camel hump castings, nicknamed for the distinctive humps in the middle of the accessory bolt holes. These featured 64cc combustion chambers and ports that Chevrolet claimed flowed 202 CFM on the intake side at 0.500-inch lift. Independent testing showed they were good for maybe 185 CFM on a good day, but that was still impressive for 1967. The exhaust ports were particularly well designed, with a smooth radius exit that helped scavenging at high RPM. But the real party trick was the intake manifold. Chevrolet fitted the Z28 with a Winters aluminum high-rise dual-plane intake topped with a Holley 4053 4-barrel carburetor. That Holley was rated at 780 CFM, massive for a 302 cubic inch engine. Most 350s ran 600 CFM carbs. This thing was drinking fuel like an engine 50 cubic inches larger. At 7,000 RPM, it needed every bit of that airflow. The carburetor had mechanical secondaries that opened based on throttle position, not vacuum, because at the RPMs this engine ran, vacuum signals were about as reliable as a politician's promise. Now, you might be thinking this sounds like a proper racing engine. You'd be right. This was a racing engine. The problem? Chevrolet was selling it to anybody who walked into a dealership with $3,100, no special license required, no training course, no warning label that said, "This engine will destroy itself if you don't know what you're doing." And most people didn't know what they were doing. Let me put this in perspective. Your typical small block Chevy of the era was designed to cruise at 2,000 RPM and rarely see the far side of 5,000. It had lazy valve timing that made good vacuum for power brakes and smooth idle for comfort. The 302? It didn't even wake up until 3,500 RPM. Peak torque, all 290 lb-ft of it, arrived at 5,300 RPM. Peak power, 290 horsepower, came at 5,800 RPM, but the engine would keep pulling to 7,000 RPM and beyond. That's where the problem started. See, that 30-30 cam created valve events that were right on the edge of what the valve springs could control. Chevrolet's engineers calculated that valve float would start around 6,800 RPM with fresh springs, but springs don't stay fresh. After a few thousand miles of high RPM operation, those springs would lose tension, the coils would take a set, the installed height would increase. Suddenly, valve float was happening at 6,200 RPM, then 6,000, then 5,800, right where you were making peak power. Valve float is when the valve spring can't close the valve fast enough to keep up with the cam lobe. The valve bounces off its seat instead of closing smoothly. In a mild engine, this causes a power loss and maybe some backfiring. In the 302, spinning at 7,000 RPM with 11.1 compression, the valves would contact the pistons. Not a gentle kiss, either. We're talking about a collision violent enough to bend the valve, crack the piston, or both. If you were lucky, the engine just stopped running. If you weren't, the bent valve would jam open, the piston would come up on the compression stroke with nowhere for the air to go, and the connecting rod would buckle like a pretzel. But valve float was just one way the 302 would commit suicide. Let's talk about those connecting rod bolts. The 1132-inch bolts were rated for 150,000 psi tensile strength. Sounds strong, right? At 5,500 RPM, those bolts were seeing about 650 pounds of force trying to tear the rod cap off every time the piston changed direction at top dead center. At 7,000 RPM, that force jumped to 1,050 pounds. At 8,000 RPM, which the engine would spin to if you missed a shift, the force exceeded 1,370 pounds. The safety margin was gone. The bolts would stretch, the cap would shift, and the big end bearing would spin in the rod. Oil pressure would drop to zero in about 3 seconds. The engine would seize solid in 5. Then there was the oiling system. Chevrolet used the standard small block oil pump, good for about 60 psi maximum pressure. The problem was oil control at high RPM. The short stroke meant the pistons were moving up and down incredibly fast, whipping the oil in the crankcase into an aerated foam. The oil pickup would suck up this foam instead of liquid oil. Air doesn't lubricate bearings very well. The main bearings would run dry, especially the number 2 and 4 mains, which fed the rod bearings. The bearing material, a copper-lead overlay on steel backing, would melt and smear. The crankshaft would weld itself to the bearing, and the rotating assembly would stop rotating, violently. Racing teams discovered this the hard way at places like Riverside and Laguna Seca, where long, sweeping corners would cause oil starvation. The oil would slosh to one side of the pan, uncovering the pickup. 3 seconds later, there'd be a rod through the side of the block. The solution was a deep sump oil pan with trapdoors and windage screens, but those weren't available from Chevrolet. You had to know to buy them aftermarket. Most street drivers didn't know. The cooling system was another weak point. Chevrolet fitted the Z28 with the same radiator as the base Camaro with the 230 cubic inch 6-cylinder. That's right, an engine making 290 horsepower got the same cooling system as one making 140. The water pump was the standard small block unit, moving about 35 gallons per minute at 6,000 RPM. Sounds like a lot until you realize the 302 was generating about 97,000 BTUs of waste heat per minute at full throttle. The cooling system could reject about 85,000 BTUs per minute under ideal conditions. See the problem? Track sessions would see coolant temperatures spike past 240 degrees. The 15 psi radiator cap would blow off, spraying coolant everywhere. The engine would run even hotter without coolant, causing the aluminum pistons to expand faster than the cast iron bores. The pistons would scuff, then seize. If you were really unlucky, a seized piston would rip the wrist pin out of the connecting rod, sending the piston crown bouncing around the combustion chamber like a pinball while the rod flailed around the crankcase, destroying everything it touched. Even the fuel system was marginal. That big Holly carburetor needed serious fuel flow, about 58 gallons per hour at full throttle. The mechanical fuel pump was rated for 80 gallons per hour, but that was at zero pressure with a new pump. Add some heat soak from those tube headers everyone installed, a few thousand miles of wear on the pump diaphragm, and actual fuel flow might be 50 gallons per hour. Run the engine hard on a hot day and it would go lean. Lean mixtures and 11.1 compression don't play nice together. Detonation would crack the ringlands on the pistons. Compression would drop. Oil consumption would skyrocket. The engine would smoke like a crop duster until it finally ventilated the block. But here's the thing. Racers expected this. They knew the 302 was a hand grenade. They'd rebuild it every few races, replace the valve springs every other weekend, run deep sump pans, electric fuel pumps, and oil coolers. They'd degree the cam to make sure valve timing was perfect, check rod bolt stretch with a micrometer, and run race fuel exclusively. Mark Donahue's Penske Racing Z28s went through 3 engines per race weekend. That was considered normal. Street drivers had no idea what they'd bought. They'd hear about this legendary high-performance engine, buy a Z28, and drive it like their cousin's 327 Chevelle. They'd lug it around town at 2,000 RPM where it had no power, and the cam made it surge and buck. Then they'd floor it from a stoplight, bang second gear at 7,500 RPM because that's what the racers did, and wonder why there was suddenly a connecting rod sticking out of their oil pan. The dealerships were no help. Service bulletins from Chevrolet warned about valve float above 6,800 RPM, but mechanics would tell customers the engine was built for 8,000 RPM because that's what the sales literature implied. Nobody mentioned that 8,000 RPM required racing valve springs that needed replacement every 3,000 miles. Nobody explained that the engine needed 15 minutes of warm-up before hard use to get the bearing clearances right. Nobody talked about the critical importance of 20W50 racing oil changed every 1,500 miles. The tuning situation made everything worse. Every kid with a wrench thought they could make the 302 faster. They'd advance the timing to 38 degrees total because that's what their buddy's 350 ran. Never mind that the 302's combustion chambers were designed for 32 degrees maximum. The extra timing would cause detonation that sounded like marbles in a coffee can. They'd lean out the carburetor to get better fuel economy, not realizing that the engine needed that rich mixture to cool the pistons at high RPM. They'd install headers without heat shields, cooking the starter and fuel lines. They'd remove the fan shroud for better cooling, actually making airflow worse. The mythology around the 302's fragility grew with every failure. Stories spread through bench racing sessions at drive-ins and drag strips. My buddy's cousin had one that threw 3 rods in a month. Guy at work had his catch fire when a rod went through the fuel line. Heard about a Z28 that dropped a valve and took out 2 spectators with shrapnel. The stories got wilder with each telling, but they all had a kernel of truth. The 302 was absolutely capable of spectacular self-destruction. By 1969, the casualties were mounting. Warranty claims were through the roof. Chevrolet dealers were replacing engines under warranty at an alarming rate, and General Motors bean counters were not happy. Something had to be done. The solution came in 2 parts. First, Chevrolet revised the valve springs for 1969, using a dual-spring setup with damper that could control the valves to 7,200 RPM, even when worn. Second, they started offering the 302 with an automatic transmission and milder hydraulic cam for those who wanted the Z28 look without the mechanical mayhem. But the biggest change came in 1970, when Chevrolet quietly discontinued the 302 altogether, replacing it with the 350 LT1. The new engine made the same 360 horsepower, but at a much more manageable 6,000 RPM. It had hydraulic lifters, milder valve timing, and connecting rods that wouldn't escape through the oil pan if you missed a shift. It was faster, more reliable, and easier to live with. It was also boring compared to the psychotic 302. The racing teams kept running the 302 in Trans Am through 1970, and it finally got the development it needed. Penske's engines used Carrillo rods with 7/16-inch bolts, rev kits that would limit RPM to 7,800, dry sump oiling systems with 3-gallon tanks, and valve springs changed every 300 miles. They made 450 horsepower and could run flat out for hours. But those engines cost $15,000 to build in 1970 money, about $115,000 today. Not exactly street-friendly. Looking back now, the 302's reputation seems almost quaint. Modern engines routinely spin to 7,000 RPM with hydraulic roller cams and last 200,000 miles. The current Chevrolet LT6 in the Z06 Corvette spins to 8,600 RPM and comes with a warranty. Variable valve timing, better metallurgy, and computer-controlled fuel injection solved all the problems that plagued the 302. But those solutions came from lessons learned the hard way, written in broken parts and blown engines. The 302 Turbofire wasn't a bad engine. It was a racing engine sold to the public without an instruction manual. It was an engineer's exercise in high RPM theory that met the brutal reality of street driving. It was a magnificent bastard that would sing a symphony at 7,000 RPM right up until it scattered its guts across the pavement. It demanded respect, regular maintenance, and an understanding of its limits. Most owners provided none of those things. Today, original DZ302s are incredibly valuable, worth more than entire cars were back in 1969. Collectors pay premium prices for date-coded blocks and original 3030 camshafts. The engines that survive are usually rebuilt with modern parts, better rods, stronger bolts, improved valve springs. They're reliable now in a way they never were when new, But every owner knows the history, knows the reputation, knows that they're sitting on 302 cubic inches of barely contained violence. The 302 taught Chevrolet that selling race engines to the public required more than just good engineering. It required education, proper support, and realistic expectations. It taught enthusiasts that factory performance claims came with asterisks you could see from space. And it taught an entire generation of drivers that sometimes the difference between legend and disaster is just one missed shift. That's the real legacy of the DZ302, not the victories at Riverside or Donahue's Trans Am championships, but the countless broken engines that proved you can't just put a race motor in a streetcar and hope for the best. It was an engine that demanded excellence and punished mediocrity with extreme prejudice. In a world of compromise and safety margins, the 302 was a reminder that sometimes engineers build something right on the edge just to see what happens. What happened was chaos, carnage, and one of the most enduring legends in Chevrolet history. What's the wildest engine failure you've ever witnessed? Drop a comment below, and if you enjoyed this deep dive into one of Chevy's most notorious engines, hit that subscribe button. Until next time, keep those RPMs reasonable and those rod bolts tight.